be starting up chapter 2. Now, chapter 2 is actually a really short chapter. In fact, like, had we scheduled out chapter 2 the way that it was scheduled out last trimester, you would have been testing, like, next week, which, like, the week we come back from break, which is only a 2-day week, you would have been testing on the second day. Like, this is a really short section. We have kind of extended that out. We're not going to quite do it quite like that. But overall, a number of the things that you're going to see in this chapter are going to be very familiar, not just to things that you did in algebra back in 9th grade, but also to things we've already done in this class. For example, today, we're starting up section 2.1. Now, we're going to be doing 2.1 over a couple of days. But today's focusing in on transformations. But today, it's only going to be of quadratic functions. We did transformations in chapter 1. The difference is that when we did it in chapter 1, we focused in on all of the different functions. Today we're going to be zoning in on the quadratics a little bit, which oftentimes makes it easier because of the fact that we're not going to be dealing with quite as many things. Now, when we focus in on transformations of a quadratic function, first off, we're going to talk about what makes something a quadratic function and something that goes with that. Quadratic function, by definition, is a function that can be written as f of x is equal to a times quantity x minus h squared plus k, specifically where a is not equal to 0. Because if a is 0, then the x's cancel out, the squareds cancel out, it just becomes a constant function. This right here, this piece of it, this a times quantity x minus h squared plus k, involves AH and K. We talked about AH and K in chapter 1. We're talking about them again today. But in quadratics, this function in its AH and K format is known as vertex form. Now, when we talked about transformations back in chapter 1, it wasn't just AH and K, though. What was the other variable that messed with the graph? B. Now, B is not a part of vertex form for a reason. Doesn't mean we don't do the things related to B, which was flipping over the y-axis, or horizontal stretches and shrinks. Those things will still happen. If we do those things, they will still happen directly in front of the x, so right here in those parentheses. The reason that B is not a part of vertex form is regardless of what B is, you can simplify a function to go back into this form, and this form tends to be easier to work with than the form where B is involved. So that's why they don't have the B there. The B will still be a thing, and we'll talk about it. It's going to slowly become less and less of a thing as we go through the sections, though. Now, before we get to our examples that we're going to do today, what do you know about a quadratic graph? known as a parabola. In other words, it has what shape? It's the shape of a U. So, today you're going to see some instructions that look familiar to things that we did back in chapter 1. We're going to do slight change in the fact that, yes, we're focusing in on quadratics. We're also going to get the calculator involved today. We're also going to change it a little bit by taking our graphs one step further, and we're going to be identifying a vertex today. G of x equals x squared plus 3. Now, I have zeroed out in my mind that there are many of you that can tell me exactly what the transformations are without having to go and look at the graph. But today, one of the things I do want to focus on is getting you to get those things in those graphs. So, we're going to grab out that graphing calculator. Okay, so when you are looking at the graphing calculators, generally speaking, you always have to get into the menu that actually fits what you're trying to do. We are trying to graph, so we want to go into our graphing menu. Now on the TI, that's the y equal to. On the Casio, you have to actually back out of the typical calculator piece, or if you're in the statistics section where it's got the lists, you still have to back out of that by going to your main menu. So click the menu button, which is right here on your graphing calculator. And we are going to go into graph. On your calculator, it might be number 3. On my calculator, it is number 5. It depends upon which Casio you have. Charging yours, you should make sure you know how to do it. Just, I know how to do it. Okay. Now, this menu is going to be the place where you're going to have issues possibly pop up on your graphs. So we have to be comfortable with working with our menus. First off, on the TI, I want you to take a look at that graph, and do you notice that above all of the y equals, there's plot 1, plot 2, plot 3? Do you notice that one of them's highlighted? Now your calculator might not be highlighted, but those plots are the calculator trying to plot data points and make our scatter plot, because that's what we set these calculators up to do. Are we trying to make a scatter plot right now? No. Which means if that is turned on, our calculator might throw a hissy fit. So we need to turn it off. Now, when we were going and setting up those statistics, we went into stat plot, but you don't have to do that when you're trying to just turn them off. If you're trying to turn any of those off, use the up arrow You could scroll left and right for the 3 plots if you want, but with the plot that's highlighted, just click enter and it will unhighlight it. That will turn it off. Other things on the TI that mess with things is every once in a while there's an equation in here, and sometimes it hides below what you can see. So I highly recommend you scroll all the way down and make sure there's no equations in your graph right now. Now Casios tend to have a different issue pop up. Oftentimes, what happens on the Casios is this variable gets changed. Do you notice my first one says y equals, but my other ones say r? That's because I literally just went in and I changed the type of graph that I was looking at. I don't actually want these to be anything other than y's. So, if you ever have a situation where it's anything other than y's, and on Casios this gets switched a lot. So even if yours do all say y's, you need to know how to change it. You need to know how to fix it if these are not all y's. And it's a real simple fix. Do you see right here, my third option says type? It means change the type of graph you're doing. So if I click F3, it'll bring up the type menu, and I want all of them to be y's, so I'm going to change the type to a y equals using F1. Now they're all y's again. If there's anything in your Casio, you also want to delete it out, especially if you've got one of the more advanced Casios. You can put 20 different equations into the calculator all at once. And if anything's typed into those graphs that is not what you want, oftentimes people accidentally put a decimal point in there and now the calculator has no clue what to do with it. Those need to go away. So with the equation highlighted, you click delete, it'll ask you, are you sure? Yeah, I want to delete it. Okay, once you got this is where you type in your equation. Now, on the TI calculator, your variable button is right here. On the Casio calculator, your variable button is right here. So, I want to type in x squared plus 3. And so I type in x, and then I do the squared, and then I do plus 3. Make sure you are not typing the plus 3 into the exponent. If it all of a sudden looks like a tiny little plus 3, then you're going to have an issue. Once you've got the equation typed in, hit either enter or the EXE, and it will set that equation in there. Casios, I want to point out one other issue that tends to pop up when people are doing this in their calculator. When I start typing something in, do you notice across the bottom it brings up some more letters, some more variables? They are not variables. Those are functions referencing variables. If you use this button for X, as I often see people do, looks like a capital X, it's not an X. Your calculator will not know what to do with it. So make sure you're not using that for your variable. Make sure your variable, you're using that X theta T button along the left side. Now, at this point, if you click graph on the TI or draw on the Casio, you may or may not see a graph. Because the other thing you have to know about your calculator is you have to know that your calculator is not always going to look at the right part of the graph unless you tell it to. If you've got a graph, in this case it's going to be U-shaped. My graph will look something like this. My TI calculator appears to be looking here. Well, my Casio, I have no earthly idea where it's looking, but it's definitely not seeing the graph. It's probably looking like right here. You have to tell the calculator where to look. Generally speaking, our graphs are for the most part going to be pretty easy to see by looking at a standard viewing window. So you got a couple ways to get that. One option is window or V window on the Casio. If you click those buttons, it will tell you what part of the graph it's looking at very specifically. It will tell you the minimum x value it sees and the maximum x value it sees. It will tell you what it is using for a scale on that axis. I don't know what dot is. I've never learned what dot is, just leave dot alone. It will tell you the y minimum, the y maximum, and if you scroll down a little bit on the Casio, it will also tell you the scale at which it's looking at the y-axis. Generally speaking, our calculators are going to be fine looking at numbers between like -10 and 10 on both x and y axis. So I can manually change these. X minimum, -10. Enter will get me to the next number. X max, 10. And you don't have to clear them out before you start typing over. It assumes that you're replacing everything that was already in there. X minimum, -10, X maximum, +10, and a scale of 1 works fine. That's what the axis is counting by. That is one way to change it. If you ever want a shortcut to it, on the TI, if you do zoom, and then you see where it says Z standard, -10 to 10 on a graphing calculator, on a TI calculator, that is considered standard. So if you ever want the shortcut version of doing that, zoom, 6 will get you there. On the Casio, once you're in the viewing window along the bottom, see where it says standard, click that button and it'll change it all. It's already at standard because I typed it in, so it didn't change anything. But had one of these been different, clicking that would change it. The TI, when you do the zoom, it goes directly to the graph. The Casio, when you're in this menu, click exit and go back to draw and you can see your graph. This is what my graph looks like. Now, it might be helpful for us to have the parent graphs in here. So I'm going to go back to where my graph is, back to my y equals on my TI. Just click exit on the Casio. And in y2, I'm going to write the parent function, which is x squared. And I'm going to go right back to my graph. And it'll help me kind of see what happened. Now, my calculator's color, so I can tell you the difference between the two is the blue and the red. The parent function always hits the origin, always opens up. What did x squared plus 3 actually do for transformation? It moved up 2. It translated up, sorry, not 2, 3. We have an issue seeing stuff on our graph. It could be this, I guess. So, this one moved up 3. Could you have probably figured that out on your own? Yeah. But that's what it did. Okay, sketch the graph. When it's a sketch, does it have to be perfect? No. Doesn't have to be perfect, doesn't have to be a large graph. The key thing I'm looking for is that it's hitting the important points. The important point on a parabola is what point? This low point, also known as the vertex. And I would probably identify that vertex as the coordinate point 0, 3. And by probably, I mean the instructions say to identify the vertex. You might as well put it on the graph. G of x is equal to a negative, parentheses, x minus 4 squared plus 1. If you want to tell me what the graph does before looking at it, go for it. If you want to look at the graph in order to see it, that's fine too. I'm going to go into y equals, I'm going to get rid of my x squared plus 3, and I'm instead going to type this in. I'll leave my parent there as a reference. Negative, parenthesis, x minus 4, close parenthesis, squared plus 1. Make sure you're using a negative symbol in front and not a minus sign. The calculator doesn't understand minus and negative, it's the same thing. For the most part, I shouldn't have to change my zoom a whole lot at this point. If I just click graph, it should show me what I'm looking for. What did this one do? Reflected across which axis? The x-axis. What else did it do? Move to the right 4. And it moved up 1. Now we haven't talked about AH and K with this, but based on what we've done already, based on what we're seeing, can you kind of see what's moving what? Adding outside of the parentheses moves up, or if it was subtracting, it would move down. Subtracting inside made it move to the right. If I was adding inside, it would move to the left. The negative in front caused it to flip across the x-axis. The key thing I'm looking for is where that vertex is and what the graph kind of looks like. Where is the vertex in this graph? 4, 1, because it was at 0, 0 for the parent, moved right 4, moved up 1. And then it opened downwards. Does say identify the vertex, so I might as well put it directly on the sketch. If you'd rather label it separately, you can do that too. I don't care if you label it on the graph or if you label it separately. Either is okay. Without directly typing it into the calculator, could you tell me what this graph is doing? Break it into pieces. I'll start with what tends to be easiest. The -4. Moving down 4. outside the parentheses, added or subtracted, is up or down. Plus 2 inside the parentheses is moving left. 2. Inside the parentheses, you got to kind of recall that inside the parentheses does opposite of what you think it should do. Isaac. Seriously. What does the 3 do? It does stretch it, but not horizontally, vertically. It's a vertical stretch factor. 3. It's going to make it skinnier by multiplying everything by 3. You can use the graph to see these things too. By looking at my graph, I can tell that it moved down 4 because I can count the little ticks. I can tell it moved left 2 because I can count the little ticks. I can also see that it's skinnier. Skinnier is either a vertical stretch or a horizontal compression. That depends upon where the number is, if it's inside the parentheses or outside. Skinny, it's over here. It's the location of my vertex. -2, -4. Don't have a whole lot left. I'm going to do this example. We're going to write some key things down, and then I've got one example that has to hit on something that we just haven't seen after we write those things down. I see a -1/2 inside. Now remember, when things are inside, they generally are going to be opposite of what you think. I'm going to ignore the negative for a little bit. Generally a 1/2 getting multiplied by things. If it's being multiplied by things, it's either a stretch or a shrink. A 1/2 typically makes people think it's a... Most people think a 1/2 would shrink things down. But since it's inside the parentheses, it's opposite of what you should think. It's not a shrink, it's a stretch. So if you thought stretch, then you were thinking the right thing. Specifically, vertical or horizontal? Horizontal. Inside is horizontal. Remember, for horizontal, the value you put in the equation and the factor are slightly different. How do they differ? They're reciprocals of one another. The number I put in was a 1/2. The reciprocal of 1/2 is 2. What does the negative do inside? What does a negative do when it's put in front? Reflects across the x-axis. What does it do when you put it across in front of just inside the parentheses, though? Reflect across the y-axis. this graph tends to be the one that's the hardest for people to picture. Make sure you're putting the squared outside the parentheses. The red's the original graph. The blue is the modified graph. Horizontal stretch, horizontally grabbed, pulled outwards, kind of flattened it down. Do you notice the reflection? No, because if it reflects across the y-axis, this is the y-axis. If it's perfectly symmetrical and you flip it around, do you notice a difference? No. It did do it, but we won't notice it. I'm going to make it look fat, and its vertex is located at 0, 0. Okay. So, I mentioned we were going to kind of summarize some things together, and then there was one more example that we had to talk about. Things we're summarizing is essentially what vertex form does. I've given you this information before. But I organized it in a different way. So I'm going to give you the information again. I'm going to organize it slightly differently, and I also know this is one of the things from chapter 1 that troubles people the most, mainly because we were working with so many different functions. Now, before I write anything about what this does, I'm also going to draw a little arrow right here, because that's where B would be. And I'm also going to write a little note. Say it will mess with the vertex. We're going to talk about a little bit of what I mean with that with an additional example at the end. I'm going to clarify that a little bit. When a quadratic equation is in vertex form, A will control two different things. If A is negative, it will reflect across the y-axis. I don't know why I started that with an F. Actually, I do. I started to write flip, but I would rather write the word reflect. Reflect across the x-axis. Now, we tend to say if A is bigger than 1 or if A is between 0 and 1, but that tends to mess with people with the negatives. So, in all technicality, if the absolute value of A is greater than 1, it's a vertical stretch. Factor whatever that A, or technically the absolute value of A, is. If that A value is between 0 and 1 in the absolute value form, it's a vertical shrink. Again, the factor is whatever that A value is, but without the negative, so it's the absolute value of it. B is the one you're not going to see as much, but it will sometimes pop up still. It again controls two things. If negative, it will reflect. This time across the y-axis. But you won't really notice it. Particularly, you won't notice it if it's done to the parent function. If the absolute value of b is greater than 1, why did I write shrink? It's not a horizontal shrink, it's a horizontal stretch. I'm apparently having a day with what I'm writing. But its factor is the reciprocal of b. A reciprocal is to do 1 over something, or to just flip the fraction. Similar to the a, if the absolute value of b is between 0 and 1, it's a horizontal shrink. Factor for horizontal is opposite of what you think it should be. It's the reciprocal of the number inside the actual equation. And to the easier ones, h and k. H and k tend to be a little friendlier. H moves either left or right. You will move to the right if you are subtracting h. You will move to the left if you are adding an h. K is up and down. You will move up if you are adding a k, and you will move down if you are subtracting a k value. Now this is called vertex form for a reason. And that's where I wanted to talk about the fact that b can mess with that vertex if there's a b involved. Now, I purposely chose ones that would not get messed with for my first 4 examples, so that we could kind of see why this is called vertex form. The original vertex is at 0, 0. When you see a +3 in the k spot, the y value changed to a 3. When we saw a +1 in the k spot, the y value changed to a 1. When you see a -4 in the k spot, the y value moved to a -4. When there was nothing in the k spot, the y value did not change. The vertex's y value will always be what that k is. Now, vertex is a coordinate point, so let's talk about the x value of the coordinate point. On the first equation, it stayed 0. On the second equation, it changed to a 4 because there was a -4 that moved it to the right. On the third one, it became a -2 because there was a +2 in the parentheses that moved it left 2. This one, it stayed at 0 because it didn't move left or right. +2, -2. -4, +4. Do you notice that vertex form has a negative in front of the h? It's designed that way because the vertex itself is technically at hk, keeping in mind that h is the opposite of the number actually added or subtracted in the parentheses. You should be able to tell the vertex of a function in vertex form just by looking at the equation. The one thing that messes with that, though, which is why I wanted to do one final example. A, B, C, D, we're on E. The one thing that messes with that, though, is still a B value. Has to do with the fact that that B value, while it only affects the X technically, vertex form will have it simplified out and pulled out of those parentheses. If you were given something in this form and you wanted to write it back in vertex form, then what you would need to do is take that 2x plus 6 and actually square it, in other words, multiply it by itself, which you'll get 4x squared plus 24x plus 36. And then it's got this minus 2. And then it would end up factoring this 4 out so that you could write it as 4 something x plus or minus something and then plus a k value here. It would then mess with this to get into this form. Now, as a result, what ends up happening is that b value, which affected things here, all of a sudden got ripped away from this as well. Here's the short of it. When there's a number here, if you want to figure out the vertex from the equation, you have to factor this out. So I take 2x plus 6, I factor that number in front out. To factor something out is essentially to divide it out, but leave it in front. If I divide 2x plus 6 by 2, I am left with 2x divided by 2 is just x, and 6 divided by 2 is 3. That means the vertex, which typically is opposite of this, same as this, will be opposite of this. This piece doesn't get affected. It's still the same as that. My vertex here would be at -3, -2. Could you figure that out by looking at the graph? Yeah, you can type this entire beast into a calculator and make the calculator do the work on the thought process. But when you do that, just understand that it will mess with some things. That is it for notes today. You're not going to see a whole lot of B, but you will see some. Okay, homework's on page 50. It is really broken up into small sections, so it's going to look a lot longer than what it actually is. 2 through 10 problems, these ones are the evens. 11 through 14 is another little section. 16 through 28 is also evens. And 33 through 38.